and this is a quick lesson video on how magnetic fields are created. So, electromagnetism, this was really cool, I think, about our universe is that, like, magnetism, this thing that, like, you don't really think about, right? It's just your, refrigerator magnets or the magnets on toy cars. Those are, like, connected, like, intimately connected. It's not like some, like, vague, connection as in, like, oh, like how gravity and, electricity have like the same like force equation, right? It's not like that. They're like intimately connected. There's a very strong, clear connection between electricity and magnetism. We found out through experiments and just by pure chance, right? Placing a compass by current carrying wire, we have found that moving charge can create a magnetic field. So if I had a proton moving like so with the velocity v, if it's moving, it can create a magnetic field anywhere in space. It could be a magnetic field at this point P. Now, if you're in AP Physics 2, you're not going to really have to worry about this. I'm going to give the equation. If you're in Physics C, it's going to be more useful. I'm going to give the equation, but if you don't understand it, because that's some weird math stuff, if you don't understand it, that's okay. You don't need to even use it. You're never going to use it ever. But basically, it says that B is equal to mu naught over 4 pi. So this is the B at point P, right? The B field, the magnetic field created at point P. Mu naught over 4 pi times Q V cross R hat over R squared. Once again, if you're in Physics 2, there's this unit vector over here, and it's like, you're taking the cross product of V cross R hat, but this is a unit vector, so it's like it only has a value of 1. So yeah, QV cross R over R squared. You can really simplify this stuff right here. This is really just, if I rewrite this to make it more AP Physics, I guess 2. But still, you will never need to know this equation. This is just for you to, I guess, kind of understand. This is just the general equation. Mu naught over 4 pi times QV sine theta over R squared. And this is the magnitude. So if you want the direction of B, we're going to talk about how to get that. Because you don't have to worry about this V cross R. There's the right-hand rule. But to find the magnitude, it's mu naught over 4 pi QV sine theta. Now, what theta are we talking about? If you were to, so let's say this is your point charge, and then I want to find so if this was R, this theta is referring to the R in between. That's how you can get the QV sine theta. So, this is like the fancy way. This is how to get the magnitude. You don't need to know this in AP Physics 2. This is just to show you that a single point charge can make a magnetic field. Now, how do I get the direction? I'll just show it with the current. It's easier with like current carrying wires. This is not really something you're going to see in AP Physics 2 at all, because it's not even on your equation sheet. By the way, that equation right there is called the Biot-Savart law. Biot-Savart law quantitatively tells you that you can calculate the magnetic field caused by a charge that's moving using that equation. But like qualitatively or verbally, it's just saying that, hey, moving charge can create magnetic field, which is pretty dang neat. What we're going to do now is we're going to look at, well, what if you have current? So current, current is really just moving charge. So it's just that example, right? Where it's like, hey, you have a bunch of positive charges. Really, the electrons are flowing. But they're all moving with some velocity. This velocity is called the drift velocity, right? These like positive charge, obviously in a real circuit, it's electrons flowing, but that's still movement. The electrons have a velocity. This velocity is actually really small to what you'd think. You'd think that it'd be blazing through it, but really it's actually kind of small. So velocity, it's moving. You can change the formula. So B equals QV. Okay, I'll say mu naught over 4 pi. Oh yeah, I'll talk about this mu naught in a second if you're curious about what that is. I'm sorry for that. Mu naught over Q V. I'll do the little thing over R squared. So cross R hat. Sorry, over R squared. So there's a current, right? So if you think about B equals mu naught equals mu naught 4 pi. One way you can kind of rewrite this is, well, velocity. Now, this is calculus, so if you're in physics 2, you might want to fast forward, or you can stick around, but you don't really need to know this, once again. This is all kind of physics-y stuff. So V, that's the derivative of position with respect to time. So I can say dx over dt. But now I have a q, right? If you think about dx over dt, treating this like fractions. Q over dt, right? This is really just current when I do q over dt. So, and let me just finish this. I'll show all my algebra. But really, you can get that B equals mu naught over 4 pi. Q, okay, wait a minute, I'm thinking through how to explain this. Q over dt, that's current, right? dq over dt, or charge per time, that's your current. I dx cross r. On your equation sheet, so what this is saying is the magnetic field caused by a small circuit element. So let's say this, so I'm going to draw this without the charges, but if you have a wire, there's a small length, right? A small length of wire that is creating a magnetic field. So this small, very small section, infinitesimally small section of wire is creating a magnetic field here and here and here and here and all over space. The length of this is going to be dx. That's where the dx is. It's just the length. So then you're going to say, well, dl. They use L for length. So xl, whatever. IDL cross r hat over r squared. But this is by a small element. I want usually the whole thing, like the whole shabam, the whole like wire, not just one element. So this actually ends up being an integral. So B is equal to the mu naught over 4 pi times the integral of I dl, where you're integrating over length. So once again, physics 2, you're probably terrified if you see an integral on your test. Or you don't need to know this. This is not on your equation sheet. Well, now this is where physics 2 lock in, because this is what's you need to know. Well, not this, but the equation. If you had a really long circular, or not circular, but if you had a really long amount of wire, that, you can take this integral, you can start from a very infinite amount of length all the way to like a very, far amount of length, or, take a limit. Whatever you need to do, you can find, or use Ampere's law. And that's outside the scope of this class. It's outside the scope of this class. Physics 2, at least, Physics C students, use your Ampere's law. Whatever you need to do, you can find that the B field, right, when you finish taking that integral, or using Ampere's law, the B field by a long current carrying wire is equal to mu naught times I over 2 pi r. Is that right? Yeah. This is right. I just, if you're in physics C, the way you get this, well, this is an intro video, so I'm not sure if you'd be there yet. But, the magnetic field by a long current carrying wire is equal to mu naught times I over 2 pi r. I haven't really explained what this mu naught is. It's the magnetic constant. This is not like some random, it's kind of cool. It's not like some random like 8.8573132 times 10 to the negative 12. It's actually just 4 pi times 10 to the negative 7. Which is kind of interesting. I mean, I guess this is still like a 3.14159 kind of thing, but you know, it's just 4 pi times 10 to the negative 7th. It's not some crazy decimal. Current of your wire, and then 2 pi r, right? R being the distance. So this is your distance, r. Yeah, so let's just take a look at what that looks like. If you have charge, all right. So if so hopefully in class you learn about like out of the page is a dot and into the page is a cross. Let's say I have current going out of the page. So it would be a dot. So I would draw this. So usually how like a test would show this is like, hey, circle for the wire, like you're looking, if this was like, imagine this, right? Look, oh my God, this demo is about to be crazy. If I had a wire and then I did it like this, that's a circle. So wire going out of the page. And then I'll draw a dot to say, hey, the current is out of the page. What would the magnetic field surrounding this look like? So just as a reminder, this is literally just what I'm drawing, right? It's the front view. Front view, what would it look like? So there's something called the right hand rule. You take your thumb in the direction of the current, your fingers coil in the direction of the magnetic field. So if you were to do that out of the page, your hands are going to be swirling around the wire counterclockwise. So as we know from this equation, the magnetic field gets weaker and weaker and weaker. I'll show that by having it more and more spaced out, but it still exists, right? So it's still going to be there, and it's all counterclockwise. So yeah, you could pick a point right here, use this equation to get the magnetic field at that point. Hopefully this kind of made sense. If you have questions, let me know. I'll explain them. Thank you for watching. I appreciate it. Appreciate it.